humanity stands on the brink of a technological revolution. Scientists have announced a breakthrough that sounds like it was plucked straight from the pages of science fiction: quantum teleportation. While it may not yet mean beaming humans to the moon or distant galaxies, the implications are no less staggering. Renowned physicist Dr. Michio Kaku recently confirmed that quantum teleportation is no longer a theoretical concept, but an experimental reality. A quantum state of light has been successfully teleported through more than 30 kilometers, around 18 miles, of fiber optic cable amid a torrent of internet traffic, a feat of engineering once considered impossible. The impressive demonstration by researchers in the U.S. may not help you beam to work to beat the morning traffic or download your favorite cat videos faster. However, the ability to teleport quantum states through existing infrastructure represents a monumental step towards achieving a quantum-connected computing network, enhanced encryption, or powerful new methods of sensing. This is incredibly exciting because nobody thought it was possible, says Prem Kumar, a Northwestern University computing engineer who led the study. Our work shows a path towards next-generation quantum and classical networks sharing a unified fiber optic infrastructure. Basically, it opens the door to pushing quantum communications to the next level. Bearing a passing resemblance to Star Trek transport systems that ghost passengers across time and space in the blink of an eye, teleportation takes the quantum possibilities of an object in one location, and by carefully destroying it, forces the same balance of possibilities onto a similar object in another location. Though acts of measuring the two objects seal their fates in the same instant, the process of entangling their quantum identities still requires sending a single wave of information between points in space. Like fairy floss in a spring shower, the quantum state of any object is a hazy smear of possibility at risk of melting into reality moments after creation. Electromagnetic waves of radiation and the thermal bumping and grinding of moving particles quickly reduces the quantum significance into decoherence if it isn't protected in some way. Shielding quantum states inside computers is one thing. Sending a single photon through optical fibers humming with bank transactions, cat videos, and text messages while protecting its quantum state is far more daunting. You might as well cast your quantum fairy floss into the Mississippi and hope it tastes as good at the end. To preserve their lonely photon's precious state against a 400 gigabit per second current of internet traffic, the team of researchers applied a variety of techniques that restricted the photon's channel and reduced the chances it might scatter and mix with other waves. We found we could perform quantum communication without interference from the classical channels that are simultaneously present. While other research groups have successfully transmitted quantum information alongside classical data streams in simulations of the Internet, Kumar's team is the first to teleport a quantum state alongside an actual Internet stream. Each test further suggests the quantum Internet is inevitable, giving computing engineers a whole new toolkit for measuring, monitoring, encrypting, and calculating our world like never before, without needing to reinvent the Internet to do it. Quantum teleportation has the ability to provide quantum connectivity securely between geographically distant nodes, says Kumar, the science behind quantum teleportation. Unlike the teleportation popularized in movies, quantum teleportation does not involve the movement of matter. Instead, it focuses on transferring information via a phenomenon known as quantum entanglement. This spooky action at a distance, as Albert Einstein famously called it, links the states of two particles regardless of their physical separation. When the state of one particle is measured, the state of the other is instantaneously determined, even if they are light years apart. Quantum teleportation leverages this principle to replicate the quantum state of a particle onto another, effectively teleporting its properties. While this doesn't involve the physical movement of the particle, it creates a perfect copy at the receiving location. The breakthroughs that made it possible. Recent experiments have demonstrated quantum teleportation over increasing distances with remarkable precision. A notable success involved transferring quantum information over 44 kilometers of fiber optic cable. While this might seem modest compared to the speed of modern internet, the mechanism of transmission is fundamentally different. Quantum teleportation does not rely on conventional signals, allowing information to be exchanged instantaneously. In another groundbreaking experiment, Chinese scientists utilized quantum satellites to achieve teleportation over distances exceeding 1,200 kilometers. These successes demonstrate the potential for quantum communication in space, paving the way for interplanetary networks and faster-than-light data exchange. A team of researchers at the University of Tennessee at Chattanooga, along with those at the Oak Ridge National Laboratory, ORNL, and utility company EPB, have successfully developed and tested the first-ever transmission of a quantum entangled signal over a commercial network. This is an important step in creating a quantum internet network that is more secure and capable than existing networks. Quantum computing uses quantum bits or qubits to store information. Unlike classical binary bits, qubits can exist in more than one state at one time, allowing combinations of physical values to be encoded to a single object. Qubits can also be entangled, transmitting information from one place to another without physically traveling the distance. Known as quantum teleportation, this is an important component of a quantum-based network. Light particles or photons can be used as qubits in their polarized forms and transmitted using existing fiber optic cables, much like classical computing data. However, changes in conditions such as wind, moisture, or even temperature can change the polarization of light and interfere with the signals transmitted. Collaborative research by scientists based at Chattanooga and ORNL worked to address these issues in the existing networks. Using their approach, the team successfully transmitted quantum entangled signals between nodes at the University of Tennessee Chattanooga campus and two other EPB quantum network nodes, each about half a mile away. This is the first demonstration of this method, which enabled relatively fast stabilization while preserving the quantum signals, all with 100% uptime, meaning the people at either end of this transmission won't notice any interruption in the signal and don't need to coordinate scheduled downtime, added Chapman. The researchers have now applied for a patent for their approach. They will work on increasing the bandwidth and compensation to achieve higher-level performance, irrespective of the environmental conditions. Applications and implications. The potential uses of quantum teleportation are vast. Here are just a few of its transformative possibilities. 1. Revolutionizing communication. Quantum networks could make latency a thing of the past. Imagine real-time communication with astronauts on Mars or instantaneous global internet connections. 2. Unbreakable encryption. Quantum communication is inherently secure. Any attempt to intercept data disrupts the entanglement, immediately alerting users to interference. This could revolutionize industries like banking, government operations, and national defense. Third, quantum internet. Traditional networks rely on cables and electromagnetic waves, prone to lag and hacking. A quantum internet would transmit data through entangled particles, bypassing these issues entirely. 4. Quantum computing integration. The integration of quantum teleportation with quantum computers could create a global network of quantum intelligence, solving problems previously deemed insurmountable. Challenges ahead. While the potential is immense, significant hurdles remain. Quantum systems are delicate, highly susceptible to environmental noise, and difficult to scale. Maintaining entanglement over long distances is an ongoing challenge. However, the rapid pace of progress suggests these obstacles are not insurmountable. All it took to derail a rally that had sent shares of pure-play quantum computing stocks soaring was a single comment from a tech CEO. When NVIDIA's Jensen Huang suggested that a useful quantum computer was likely decades away, shares of IonQ, NYSE, IONQ, and D-Wave Quantum, NYSE, QBTS, fell off a cliff. As of midday Tuesday, both stocks were down at least 45% from their recent highs. Quantum computing is a technology that has tremendous long-term potential, but no one has yet cracked the code on how to successfully apply it to real-world problems. By taking advantage of bizarre quantum properties, quantum computers can complete certain types of computations exponentially faster than traditional supercomputers. So far, though, existing quantum computers have only been able to speed up calculations that have no practical applications. If useful quantum computing is truly decades away, large tech companies with deep pockets are much more likely to still be around when the technology matures. Betting on IonQ or D-Wave is ultimately a bet that a breakthrough is right around the corner, the odds of which are vanishingly small. A fanciful forecast IonQ generates a small amount of revenue from various partnerships and deals, which totaled $12.4 million in the third quarter of 2024. The company sells various quantum computing systems, but these aren't used for solving real problems. In fact, IonQ noted in its third quarter report that its recent deal with AstraZeneca was the first time the company had partnered for a production use case. Following the stock's collapse, IonQ CEO Peter Chapman released a statement regarding the company's long-term prospects. Chapman noted that global quantum computing investments had reached $50 billion by the end of 2023 and expected IonQ to be profitable, with annual revenue approaching $1 billion by 2030. Missing from the statement was any detail on how the company would achieve this. IonQ will need to build a quantum computer that can solve real-world problems faster than traditional computers within the next few years to hit this forecast. That seems highly unlikely. IBM, which has been working on quantum computing for decades, has set a timeline of beyond 2033 for supercomputers that pair quantum computing with traditional computing to tackle real-world problems. How quantum these supercomputers will be is an open question. IonQ is still valued at about $6 billion, an incredible price to pay for a company that's largely doing science experiments. Narrow use cases. When NVIDIA's Huang made his quantum computing comments, D-Wave CEO Alan Baratz shot back by saying he was dead wrong. While Baratz acknowledged that universal quantum computers, the kind theoretically capable of running any quantum algorithm, may indeed be decades out, he noted that D-Wave's annealing quantum computers were already proving useful to businesses. Philosophical questions and ethical concerns. Quantum teleportation doesn't just challenge technological norms, it raises profound philosophical questions. If a particle's state can be perfectly replicated elsewhere, are the original and the copy identical in every way? Could this principle be applied to larger systems, even living beings? Would the teleported version maintain the original's consciousness, or would it become a new entity? Moreover, the ethical dimensions of this technology cannot be ignored. As with any powerful innovation, there is potential for misuse. A quantum arms race could emerge, with nations seeking to gain strategic advantages. International cooperation will be vital to ensure this technology benefits humanity rather than exacerbating global inequalities or conflicts. A new quantum era. The advent of quantum teleportation is more than a scientific milestone. It is a paradigm shift. It challenges our understanding of time, space, and reality itself. Whether it leads us to a utopian future of instant communication and exploration, or introduces unforeseen challenges, one thing is clear. The era of quantum teleportation has begun. The journey into this extraordinary frontier will reshape our place in the universe, pushing the boundaries of what it means to innovate, explore, and exist. In a groundbreaking advancement, scientists have unveiled successful demonstrations of quantum teleportation, a technological marvel that promises to reshape the future. Beyond its technical brilliance, quantum teleportation offers profound possibilities for addressing humanity's greatest challenges, revolutionizing fields like medicine, energy, and communication. A new frontier in science. At the heart of quantum teleportation lies the phenomenon of quantum entanglement, a concept once described by Albert Einstein as spooky action at a distance. When particles become entangled, the state of one particle instantaneously determines the state of its counterpart, regardless of the distance separating them. This defiance of classical physics has opened the door to instant communication of quantum information. In 2017, researchers made history by achieving quantum teleportation over 1,200 kilometers, using China's Michus satellite. This remarkable feat demonstrated the feasibility of long-distance quantum communication, laying the groundwork for practical applications that extend far beyond the laboratory. Transformative applications. Quantum teleportation is not mere science fiction. It holds transformative potential across various domains. Medicine. By enabling the secure transmission of sensitive patient data, quantum technology could lead to groundbreaking advancements in diagnostics and treatment. Energy. Optimizing energy grids with quantum technology could facilitate more efficient use of resources, contributing to the fight against climate change. Cybersecurity. Quantum communication systems, virtually unhackable due to their intrinsic properties, could safeguard vital sectors like banking and healthcare from cyber threats. Additionally, the development of a quantum internet, powered by entangled particles, could revolutionize global connectivity, providing unprecedented speed, security, and computational capabilities. Philosophical and ethical implications. While the potential of quantum teleportation is thrilling, it also raises profound questions about identity, consciousness, and existence. If quantum teleportation transfers only information and not physical matter, does it create a perfect replica or transport the original entity? Would a teleported human retain their essence, or would they become an indistinguishable copy? These dilemmas, once confined to science fiction, now demand real-world consideration. Furthermore, the potential militarization of quantum technology poses risks of global destabilization, highlighting the need for international cooperation and ethical governance. The cosmic perspective. Quantum teleportation's implications extend far beyond Earth. For space exploration, it could enable real-time communication across vast cosmic distances, revolutionizing mission efficiency and opening new possibilities for navigation and discovery. Quantum networks in space could integrate terrestrial and extraterrestrial systems, paving the way for humanity's expansion into the cosmos. Such advancements could also deepen our understanding of the universe, allowing us to probe mysteries once thought unreachable. A call to action. Mikio Kaku, a renowned physicist, describes quantum teleportation as a stepping stone toward transcending humanity's limitations. Yet realizing this vision requires unprecedented collaboration, innovation, and ethical stewardship. It challenges us to balance our capacity for discovery with the responsibility to ensure a just, equitable, and sustainable future. As we stand on the brink of a quantum revolution, the choices we make today will define the trajectory of human progress. Quantum teleportation is more than a technological breakthrough. It is a mirror reflecting humanity's potential for greatness and its capacity for hubris. The journey into the quantum realm has only just begun. As we unlock the secrets of the universe, we may discover that the greatest mysteries lie not among the stars, but within ourselves.